So in this section of the applet, the entirety of three-dimensional space that you see, and the various objects that you might see within it, are a projection from a hypersphere in 4 dimensions that we can't see. So whereas in 2 dimensions, we had the crutch of actually knowing what 2-dimensional space was, then on the right here, there's the image just of the projection. And in 3 dimensions, we had the crutch of understanding a 3-dimensional sphere, and then in the upper right here, there was the view just of the projection. We don't have such a crutch for a hypersphere, since that's beyond our perception, or beyond my perception at least. I can't speak for you. Now the controls in the upper left here are set up specifically to be able to play with quaternion multiplication, which we'll get to in just a moment, but right now all we care about are individual points. Nevertheless, it might be a little helpful if I talk through what we have up here. So there's one quaternion, Q1, which is a point in 4-dimensional space, and similar to what you saw before, if you try to change its coordinates, it's always constrained to have a unit length, meaning the sum of the squares of these numbers is 1. And then we have some other point, P, where you can select various options for which point you want to see, or maybe collections of points, like a whole circle along the hypersphere, or a whole sphere of points on that hypersphere. And the letter P is just meant to denote one of those points. And then Q2, some other quaternion. And what you're looking at is the output of the product Q1 times P times Q2. And again, later on we'll talk through what quaternion multiplication does and how to think about it. And you'll see why setting things up this way with Q1 and Q2 sandwiching the point P is useful for understanding how quaternions relate to 3D rotation. But right now, the only thing we need to do is focus on a single point, a single quaternion, to get a sense for what the stereographic projection is doing. So Q1 will be that quaternion that we want to look at, and the only point that I'm going to show for P in the middle here is 1, and then Q2 we're going to leave that fixed at 1. So when you look at the output of this function, Q1 times P times Q2, it's Q1, some 4-dimensional point, times 1 times 1, so it stays the same. Take a moment to do this. Change the various 4 coordinates, the real part, the I part, the J part, and the K part, and see what that does to our point and where it ends up in 3-dimensional space. What you might notice in doing this is that the I, J, and K part seems to control the direction for where this point is away from the origin, and then the real part controls how far away it is. When that real part is close to 1, you're really close to the origin. And when that real part is close to -1, you're close to the point at infinity, which is to say you're far away from the origin. And this should feel very analogous to what was happening in 3 dimensions, where maybe we view this sphere from head on to notice how the imaginary parts give us a direction away from the origin, and then the real part tells us if we're close to the north pole of that sphere, which gets projected into the center, or if we're close to the south pole, which gets projected to the point at infinity. And as you change this value, Q1, see if you can kind of predict a little bit how that change is going to influence where the point F1 is.